Webcast is now starting. All attendees are in listen-only mode.
Hello, this is Dr. Bill Curtis, Executive Director of the Consortium for IT Software Quality speaking. CISQ is a special interest group associated with the Object Management Group, or OMG, chartered to create international standards for measuring size and quality from source code. As a result of that, we want to present a seminar today with Girish Seshagiri on the way he uses measures and the work they're doing at ISHPI. I want to thank you for attending the webinar called Reducing Software Vulnerabilities, the Vital Few Product and Process Metrics. So this will be a combination of how metrics fit into a very unique development process, one that has proven to be very effective. In fact, Girish was one of the original pioneers really using Watts Humphrey's personal software process and team software process and proving that those techniques were extraordinary in their ability to produce high quality software on time. Girish is the Executive Vice President and Chief Technology Officer at ISHPI Information Technologies. He's going to show how the impact of high maturity processes combined with disciplined agile teams can help create more secure, higher quality software. Now we'll have time for question and answers at the end of Girish's presentation, and to submit questions, please use the questions tab in the GoToWebinar toolbar. My associate Tracy Berardi will be managing the questions later on at the end of this presentation. If you want a PDF of the presentation, you can download it. Go over to the Handouts tab in the GoToWebinar desktop there, and you can pull down a PDF version. If you can get it now, you might be able to follow along in the presentation. So, Girish, the floor is yours.
All right, good afternoon, everybody, and Bill, thanks for that introduction. My thanks also to CISQ for hosting this webinar, and thank you all for attending. Big shout out to Tracy for coordinating the myriad details for this webcast. Bill, we've known each other for quite some time now, and for those of you that don't know, Dr. Curtis is an icon for many of us since the early days of the process improvement work. I remember going to conferences and attending his talks and learning a lot. And Bill, if you recall, in those days, we used to go around wearing buttons that said, in God we trust, everybody else brings data. And here we are to talk about metrics. So again, thanks for your contribution and your friendship. The topic is, as you see here, what are the measures and metrics that helps us to reduce software vulnerabilities in the software code? And we'll focus on the vital few because our software teams are busy people. And the last thing we should do is to impose on them the collection of what we call trivial mini data that really doesn't help the teams deliver products without vulnerabilities on predictable cost and schedule. So that's the talk. And before I begin, let me say that when I say software in this talk, for the most part, I'm referring to software application development with agile teams. So go on to slide 2. I listed here the main points, the takeaways, if you will, for this webcast. It is now pretty much understood that software with defects is insecure. And software is defective because of the poor quality process used to develop software, as well as the fact that the engineers are not specifically trained to do very high quality work. So we have quality problems, and if you have a quality problem, now it's become a security problem. So I'll be making the case that quality and reducing software vulnerabilities should be the #1 goal for every agile software team, and also demonstrate in this talk how to manage software by managing software quality. And the reliance on, in software, we have this common misconception that if it passes tests, it must be okay. And this reliance on testing as the principal defect removal method is the root cause of what I call a deliver it now, fix it later culture in software development, as well as the resulting unacceptable increases in technical debt. And I myself call technical debt as malpractice. And we also have an increase in total ownership cost of the delivered product. If you add the development cost, if you add the maintenance cost to development cost, the total ownership cost continues to increase in many Agile projects. Finally, I'm basically proposing that we in the software industry transform to a management culture, as we have did in our organization, where Agile team members are trained, certified, and empowered to do quality work using optimizing processes that relies on the discipline of high maturity practices. And the transformation needs to happen at the organization, team, and individual levels. I also want to begin this talk by generally talking about what I think is a very unique point that we are in software, and that we'll see in this next slide, slide 3. As you see here, unique point in time, and I think most of us work in software, we're excited about the work we're doing because without this work, we will not have the standard of living in the world today. But at the same time, we need to understand that software works most of the time, but because it does work most of the time, we can't declare victory because the data now shows that 90% of successful cyber attacks result from attackers exploiting defects in the software code, the defects that testing or scan analyzers did not find. And these attacks are increasing. And it's also now estimated that we're going to spend about more than $170 billion in the next 3 years on cybersecurity. And I suspect that the majority of that spend will be for what is now the reactive approach to cybersecurity, or what we may call the patch and pray method. The opportunity we now have, I think, is to be proactive and improve the quality of the software process and practically eliminate cybersecurity vulnerabilities. And then if you take a look at the Internet of Things, with 50 billion devices coming online, almost all of them with software in it, and everything from cars, medical devices, including pacemakers and stuff like that, the cyber attacks are beginning to impact personal and physical safety. So there's tremendous opportunity to improve our work so that we can prevent that from happening. And if you look at government, many federal agencies are totally dependent on legacy software for achieving their mission, and legacy software is insecure. So there's a great opportunity to modernize legacy apps that we should be working towards. So in the next slide, we have a few more things about why it is a unique point in time. In 2015, the GAO, the Government Accountability Office, some people actually call them as the people that come after the battle and shoot the wounded. I'm just kidding. And those people added the management of IT acquisitions and operations to the areas of high risk to the government agencies. That was kind of like a wake-up call for both the acquirer as well as we providers. And many agencies seem to be convinced that the way out of this is through this Agile Scrum methodology as a silver bullet solutions. And I think most of us know that there really aren't very many silver bullet solutions out there. And if you look at where the government is spending, the $80 billion annual IT spend, on average about 70% or $56 billion is going to operations and maintenance, and only $24 billion for new development. And the majority of the maintenance spend is towards corrective maintenance or fixing stuff that should have been right in the first place. So in other words, you can say that the taxpayer is paying about $25 billion a year for poor quality software. So another tremendous opportunity for us to improve this. And if you look at published reports such as the Chaos report, if you've seen it from the Standish Group, or other data gurus like Capers Jones that they put out this state of software practice and so on, you can kind of make the case that, supported by their data, they're showing that the software project management capability across the board has not substantially improved since the beginning of time. So we have another opportunity there. So the reason I kind of want this as a unique starting point here is that I think we have a choice. We can be bold and outrageous and solve problems that have persisted from the beginning in software engineering. And it's kind of what I want to kind of quickly mention to you on this next slide here. What I call the software engineering's persistent problems. And as I said, the cyber attacks are increasing due to defective software. and that continues to go on. And our large enterprise resource planning and applications like that and modernizing legacy systems invariably tend to be failures when it comes to whether did they meet their cost, schedule, and quality goals. And then if you take a look at where the software teams are spending their time, you'll find the majority of the time is spent on making this stuff work in the first place, which is by spending the time on finding and fixing bugs, which we call, in most other industries, would call scrap and rework. And you'll go out of business in most industries if that's your #1 cause. And the primary reason for all of this, in my way of thinking, is that our teams are almost always working on schedules that somebody committed them to, but they know they're not going to meet that. And in some cases, even the managers that committed them probably know that they're not going to meet that. And what I call these arbitrary and unrealistic schedule imposed on the teams with little or no input from the people who are doing the work. So they do the best they can, and when the time comes, they deliver it, and leaving the bugs to be fixed in future sprints, increments, and releases. And that's the deliver now, fix later culture that I talked about earlier. On slide 6, the next slide, we see that, well, we know that we do have methods that work, but they don't seem to scale even for medium-sized systems, let alone large system of systems. Another persistent problem is we don't have a pretty good handle on the impact of variation on individual productivity. And I'll submit to you that management and the engineers themselves really don't understand the causes of variation or how to control them. And yet we have to make commitments to deliver on certain time and within cost. And above all, engineers are frustrated when management does not respect them as individuals and ask for their input regarding things such as how long a task should take, or whether product is ready to be shipped, and so on, and turned over to production. So nobody likes to work on Death March project, and yet that seems to be the norm in many software teams. So the question now becomes then is, how do we manage software such that it's extremely high quality and predictable cost and schedule, and most importantly, secure from cyber attacks? And as Bill mentioned, what I'm going to be doing is sharing what we did and how we did it, and I think what every organization can start working towards that goal now. So with that background, so let's discuss how we should manage for secure software development. And one of the reasons we have quality problems, and because of that, which turn out to be vulnerabilities, is that, as I mentioned before, our developers are not trained to do quality software work. So we need to make sure that we will train every member of our software team in things such as estimating the sizes of products they're building, planning and tracking their work, and measuring and managing the quality of their work products. I think you'll agree with me that these are not things that are currently taught in almost all computer science degree programs, as well as many software engineering degree programs in universities. So we need to make sure that those of us that are in the business of managing these teams actually make this training to happen. Then we need to make sure that each project is started right, and the team is a gelled team from the get-go. In many Agile projects, what I see are working group under a single leader, and that's not a team. So in the transformed state that I think we should be at, which is where we went through the journey and got there, was every team is a true team where the team members are empowered to make commitments they know they can keep, because they've been trained to negotiate, trained to make estimates based on their own historical data, and they know what they can achieve, and they negotiate that commitment. And then the team sets up goals, and I'm proposing that going forward, we make sure that every team, #1 goal is to reduce software vulnerabilities, because we address the quality problem there, and then all of the other issues sort of kind of work their way because of that. And so we need to get our teams to make commitments for cost, schedule, and quality based on historical data. And when you do that, you get a gel team, and you'll be amazed at what they can do. So, so what happens, as I said before, this would be on on slide 7. So one of the misconceptions in software, as I said before, is if it passes tests, it must be okay. And if testing is the only defect removal method, what you expect is, what you probably will get is a patched up product that works as long as you stay within the same paths that were in the test. Instead of that, what we need and what our organizations should try to get are engineers who are trained to remove a very large percentage of defects before test by personal and peer reviews of the work products. And every engineer should make sure that the components that they build are defect-free in integration systems and acceptance tests, and have zero violations have zero cybersecurity vulnerabilities, as well as zero violations in the CISQ security characteristic measures that I'll talk about later. So slide 8, again, so continue to talk about managing for secure software development. The CIO of NASA once said that up to 60% of the applications do not pass independent penetration tests for what we've known for a long time as known vulnerabilities or weaknesses, the top 10, the top 25 most dangerous programming errors. This, I think, this is not acceptable, and we need to change this. And the way we do that is by making sure that these are in the review checklists, which are used by the individual engineers on the teams to make sure that before they even go into test or submit the code for scans and analyzes, that they're already taken out. So the other thing that managers need to do is to support the teams to collect, analyze, and report lots of data to report the product, the vital few product and process data. And again, we don't want to burden our teams with lots of data. So in our case, we only ask them to collect 4 things: size, effort, schedule, and quality data. And you will see here when they start collecting that and the kinds of metrics that we can derive from that, what they can do with it. And remember, quality without numbers is just talk. So we have to make sure that when we describe quality, we can describe that with actual data. Finally, to manage secure software development, we need teams to report team status every week with very precise and accurate data on what was the planned size and what was the actual, planned effort, what was the actual, planned schedule against actual, earned value, and so on. Same with the defect data. Where did the team plan to inject the defects? Where were they actually injected? Where did they plan to remove it, and where they were actually removed? This is enormously valuable data that gives a pretty good insight into the development process and whether or not it had quality in it or not. And in many Agile teams, what I see is they do report status in daily stand-up meetings, but most of the time it is not very precise and it's kind of vague. And then contracts require only a monthly status report, which are usually too late and of little value to the team that is doing the work. So, you know, we do recall that Fred Brooks once said that projects get to be 1 year late, 1 day at a time. So timely information is very critical. And if we start managing quality, the teams will actually use the data for themselves, and they'll try to make sure that they are building a quality product and building security in from the very beginning. So you can by now you probably get the drift of what I'm talking about is not a technical solution, but a new philosophy of managing software teams by managing software quality with empowered engineers and teams who have used precise and accurate data on the development process and the delivered product. Slide 9, I do want to take a few minutes to talk about the CISQ quality characteristics measures and another of Dr. Curtis's many contributions to our profession. And I want to take a minute to relate how the vital few metrics I'm proposing are related to the CISQ measures. As you see here, the question is, what attributes should be measured? And CISQ has proposed the 4 measures: security, reliability, efficiency, and maintainability for the attributes such as the ability to prevent unauthorized intrusions and data theft, which is the focus of what we're talking about here today, and corresponding business outcomes such as customer confidence, lost revenue, cost of ownership, etc. So not only did they do that, CISQ actually also defined a set of violations that can be assessed by analyzing the software code and the architecture, which is what you see in slide 10. And here you see coding violations such as SQL injections, cross-site scripting, and buffer overflow are related to the security measures. Or if you're down at the bottom, you see things like dead code and hard-coded literals impacting maintainability. And in CISQ, we have a proposal that actually the numbers of possible violations are included in there. And I think, and Bill has also, I believe, proposed that these violations or their absence can be written service level agreements between the acquirer and the provider, and that is great, and we fully support that. So now, with this background, now go ahead and talk a little bit more about the actual metrics itself with some real-life examples of the business outcomes that we have achieved when we manage software by managing software quality. And the point is that you can look at the vital few metrics that I'm proposing as the leading indicators, and the CISQ measures as the final outcome as seen by the customer. And the transformation challenge is to maintain a constancy of purpose and manage the software work by managing software quality and reduce or practically eliminate software vulnerabilities. And with these kinds of assessments that becomes more and more of a standard, our challenge as an organization is to outperform competitions in terms of these characteristics, measures, and violations. So let's now talk about the metrics themselves. In slide 11, before we begin to talk about the metrics, I do want to talk a little bit about what are some known principles that we found are extremely important to actually run a successful metrics program. Number one, most organizations, or many organizations, start by first focusing on metrics. And I suggest instead that the organization and the teams should start with well-defined business and project or team goals. And the metrics can be derived by asking the question, what do we need to know to make sure that we're achieving our goals? As for instance, what do we need to know to make sure we achieve our goal of very low or zero defects in delivered software, which in turn reduces or practically eliminates software vulnerabilities? And so, and then, as mentioned before, we need to be focused on the vital few and not the trivial many. Another important thing is that we need to make sure that raw data is normalized by size for analysis, decision making, and continuous improvement. So a size metric is make sure that our teams can collect that. And many organizations do not have precise operational definitions of the data being collected. And I'll show an example of, in the next slide, what those look like. But most importantly, the principle is, if the data is not collected and used by the team members, it will not be useful, and probably the metrics program itself will not endure. And the very last point is extremely important, is never to use the defect data for performance appraisals. So on slide 12, we have the operational definitions of things that we actually use: scheduled deviations, acceptance test defect, cost of quality, defect density, earned value, first time right in acceptance tests, peer review yield, and personal review yield. So this is just an example of the kinds of things where we have a very short and concise definition that everybody knows and is familiar with, and they're become an organization standard for the derived metrics, particularly for these derived metrics such as the cost of quality, defect density, etc. So we must follow these broad principles, and we must have operational definitions, is the point I'm trying to make there. So let me now start talking about the vital few metrics that our engineers collect. These base measures are the only 4 things they collect as they go about the task of building their work products: size, time, defects, and task completion. So we use lines of code to measure size. Our engineers record time in minutes and the number of defects throughout the life cycle phases where they're injected and where they're removed, as well as they record the task completions. So we ensure precision and accuracy by defining coding standards for every language that we use. We record the time in minutes, and only when they are spent on project-related tasks and not on non-project tasks, including interruptions and meeting times and so on. And when you start doing that, you realize that in a 40-hour week, the actual task time is only like 17, 20 hours and so on. And once you know that, then you can start working on improving that. And now we're seeing in our organization up to 30, 35 hours per week that are totally devoted to tasks. And defects, you need to have some kind of a defect classification scheme, and we use an industry standard orthogonal defect classification scheme. And then we also plan our project plans, our individual plans are granular, then most individual tasks are under 10 hours so that each engineer gets at least 2 task completions to report in weekly status meetings. So these are the important things to think about as you go about introducing the metrics programs. And we're recommending that these are 4 basic things that everybody should collect. Slide 14, we have a matrix here of the vital few metrics that you see as these 8 rows here. And 5 of them are plan versus actual, size, effort, schedule, earned value, and defect profile. And then the last 3 are total cost of quality, first time, right, and acceptance test defect density. So, so for each metric, we have you see the 2 columns there, leading indicator, lagging indicator. So we flag whether the metric is a leading or lagging indicator. Leading indicators are what you would see early in the life cycle and helps us predict what's likely to happen in later stages. The rightmost 4 columns indicate where the metrics are used at the organization, project, increment, or component levels. For instance, engineers do the review of the plan versus actual of size, time, and schedule, along with review of the defect profile at the completion of unit tests, what most organizations will refer to as the code complete stage. Similarly, the teams will review all the metrics for every increment delivery, and 7 out of the 8 at project completion, as well as the organization's process group, which periodically reports to management on 7 out of these 8 metrics. In our case, it's a quarterly meeting that we have where the process people report to senior management as well as all the project teams where we are. So the data that's analyzed at the component and increment levels are used to predict what will happen at the project and organizational levels for things such as cost of quality, first time right and acceptance test, and defect density. The point is this: if teams have a goal of reducing vulnerabilities in the code, and we know what the organization's process capability is, you need to track these things to make sure that the vital few metrics throughout the life cycle to make sure that you're actually making progress towards achieving the goal. And if not, what corrective action you need to take to be able to do that in a timely fashion. And this we should be able to do for every project, regardless of the customer domain, who the project lead is, and so on. And the true organization capability can later be validated with the CISQ quality characteristics, violations, assessment, and methods like that. I also want to talk a little bit about, in slide 15 here, as to how actually the teams use in our company some of this actual data as they go about completing their project work. They use this throughout the life cycle to make sure they're achieving their goal of reducing vulnerabilities and delivering quality. For instance, if actual size, effort, and schedule deviate from the plan, they'll start looking to see whether the process was followed, and if not, why not? Did it take more time because rework was more than planned, because the review processes were not effective? What was the cause of that? Some other kinds of questions they ask, and then try to analyze and take actions to mitigate those. If actual earned value deviates from the plan, the teams would review to see Was it because the hours worked were less than the plan, or was it because some task could not be started or closed due to dependency on other tasks and things of that nature? And all this happens weekly in the weekly status meeting, with the teams actually doing it themselves without any management involvement. And part of the project planning that our teams do, they do create a defect profile based on historical data, where the defects will be injected, and these would be the actual doing phases like requirements, design, and code, and where they'll be removed, like the removal phases like design review, code review, and all the test unit integration systems and acceptance tests. So by analyzing the plan versus actual defect profile, it gives a good indication how much the process was followed, whether the process was a high quality or poor quality. And then at the component level, teams can make a decision as to whether to proceed with further testing or send the work product back through the review stages. Also, the teams do perform what-if scenarios using the process performance model, which is a high maturity practice from our CMMI Maturity Level 5 appraised organization process. So, so this is some of the idea that you have in terms of the data that our teams collect, when they collect them, how they review them, and the kinds of decisions that they make, mostly without management involvement. So the point is that there's no better competitive weapon than self-managed teams do the work and finding joy in their work that they're doing, and that's what we see. I want to contrast this kind of data gathering analysis with this on this slide, slide 16, where you're seeing a thing that I found in a presentation from an organization about how that organization manages Agile Scrum projects. And it may not be what all Scrum teams to do, but I think it's very typical as far as I can tell, somewhat typical. According to this organization, management reviews weekly summary information on cost, schedule, risks, and issues, and project teams review daily using the Scrum process to identify and address issues, clarify, validate business requirements, and provide true project status. As you can see, the focus here is strictly on schedule, and by measuring things and reporting things such as release and increment burn down, velocity, etc. As far as I can see in these things, there's no quality information that is actually reported. And by the way, in most projects, schedule problems are normal, and because there's a poor quality development process that impacts schedule. If you don't pay attention to quality, what typically happens in many projects is that schedule problems end up as quality disasters, as we've seen happen in some recent high-profile project failures. So the other consequences are vulnerabilities in the code, increased maintenance costs, and unacceptable technical debt if you don't pay attention to quality. So the next few slides, I want to share with you actual data from our organization on the vital few metrics. Data covers from 1998 to present, showing what we call our constancy of purpose. So slide 17 and the next couple of slides that you will see, the x-axis will be the time axis, and the y-axis as the business outcome. So each data point that you see here is a project phase plotted against the start date of the project or the phase. So in this case, it's schedule deviation, going all the way back to 1998 on development projects. The y-axis is the percent deviation in committed schedule in actual number of calendar weeks versus plan as a percent of plan. So you can see the impact when we introduced the SEI team software process that Bill mentioned in the 2001-2002 timeframe. And in 2005, when we integrated the high maturity CMMI Level 5 process with the team process for what we call the Agile high velocity development process. And over the years, you can see that the teams have been consistently delivering new development projects on or close to committed schedule. and it's like 3% deviation on average from committed schedule. Tremendous improvement over an average of 50% during 1998 to 2001. And it's interesting to note that the average schedule deviation in industry today is around like 50 or 60% as reported by, again, groups like the Standish Group and so on. And it continues to be in many organizations where the only goal for project teams is to deliver on committed schedule, and yet many of the same organizations do not maintain the records and show their performance graphically over a long period of time, as I've seen it, as we're doing it here. Slide 18 is deviation, effort deviation. This is time, and this is a control chart that's measuring the effort deviation, actual versus planned number of person weeks of effort as a percent of the plan, going all the way back to 1998. And here again, you kind of see some of the same kinds of things, the impact, the positive impact of the TSP and the Agile high velocity methods, where now we're delivering on average with less than 11% deviation of committed effort, tremendous improvement over the 50% where we were at back in 1998. On slide 19, I would like to share with you the acceptance test defect density, which I think is one of the critical metrics that we have here. This is our maintenance and enhancement work, and this goes all the way back to 2002. So you can see here this organization now has a track record of delivering to the customer for acceptance testing very high quality maintenance enhancement releases with an average defect density of 0.26 defects per 1,000 lines of code, or 26 defects for 100,000 lines of code. So if you accept the published data that 1 in 20 or 5% of defects are vulnerabilities that attackers exploit, this translates to roughly slightly more than 1 vulnerability in the code per 100,000 lines of code, which is what we expect the best-in-class companies to achieve. It is a little higher than what we have experienced in our development projects, the point here being that maintenance projects we're dealing with legacy code, which is usually of lesser quality that we have to deal with. So you get some idea of the kind of record keeping and data that teams use and we use at the organization level. Slide 20, I want to share with you from one of our projects a profile of actually where the defects were injected and where they were removed. And our practice has been to make sure that the engineers put the highest quality possible code into test, and that they should strive to remove 85 to 90% of the defects before they go into integration systems, acceptance, tests, and so on. So what you see here on the x-axis are the actual phases, like critical design, personal review, critical design inspections, rework from that, and then the code review, code inspections, rework from that, and so on. And then the test phases. So you can see obviously the defects are injected during design and code, but they are removed, most of them, by the time we get to test, and that's what you're seeing here. And I think this is a good way of making sure that the Agile method, the teams, including the high maturity practices, are actually doing and producing the results that the process is capable of producing. And the last one I want to share with you is, which is on slide 21, the cost of quality. And you know that we talked about the fact that the #1 cost in software is the cost of finding and fixing defects. And one of the reasons is that, again, there's a common fallacy or misconception in software. It kind of goes like this: faster, better, cheaper, pick any 2 of the 3. Well, we can't give you all 3. Well, and this is because many managers believe that in software, quality adds to time and cost. And as you can see from our data, and this one would to substantiate this, that actually quality reduces cost. In fact, what we say in our organization is, if a customer says they want it in the worst way, we say that's the way we're going to give it. The real point is that many managers who believe that quality adds to time and cost have really no real data to back it up. And if they do like this cost of quality kind of data, they'll pretty soon understand that the more time you spend in things like appraisals, like we'll talk about here in a minute, then you actually reduce the failure and the rework cost, and you will get by much more than the actual time you spent in the appraisal and prevention. So that's the definition of cost of quality. As you can see in the right-hand column, the cost of quality is the sum of the cost of appraisal plus failure plus prevention. And appraisal is the time spent in finding defects in personal reviews, peer reviews, and all levels of first-time test execution. And failure is the time spent in rework from reviews and tests, as well as time for regression tests and so on, which scrap and rework basically. So you can see that we're continually reducing this cost of quality since 2009, and from 40% down to 32% currently on average. So, and our failure costs are less than 10, 11%, and which is still higher than what we would like for it to be, but and also compared to other industries, but is far superior to software industry averages, where the average cost of test and rework is in excess of 33, 40%, something like that. So we include cost of quality as one of the vital few metrics, and you'll see that much of this is derived from those four things that teams collect: size, effort, defects, and task completion. So that's basically what I had. I do want to show in slide 21, I'm sorry, slide 22, the same metrics in a summary chart with the three columns here that you see, industry average, best-in-class average, and the organizational average. And so this is sort of like a benchmarking the organization data against industry as well as best-in-class averages. The similar 7 rows of metrics here: scheduled deviation, acceptance test defects, and delivered product for 100,000 source lines of code. What % of design and code is inspected? How long does it take for the customer to accept the 100,000 line of code product through acceptance test? What % of defects are removed prior to system test? And what % of development time is in rework fixing these defects, and what the cost of quality is? So what I'm proposing that as in the transformation that we need to see happen is organization actually collect and maintain this data and actually benchmark themselves against industry data so they can continually improve. And again, these are the vital few metrics that we think are important. And slide 23, now let's talk about the benefits that the customers see from what we do in terms of this optimizing product development. One obvious one is that they see the working software sooner, but they'll also benefit from very high quality code with very little or zero vulnerabilities in the code, and have the confidence that the software will be secure from cyber attacks. And because of the high quality development process and the team's commitment to deliver software with very little defects, their O&M spend will be reduced significantly, and in some cases will be more than half. The reason is that teams are no longer relying on tests as the principal defect removal method, and engineers negotiate realistic schedule commitments. They achieve their personal goals that more than 90% of the components will be defect-free, and customer will see fewer bugs to fix in production and free up scarce maintenance dollars towards enhancements and not corrective maintenance. And they can draft service level agreements with CISQ assessments of quality characteristics at a higher level of confidence. You can expect vendors to provide extended warranty against defects. So now I'd like to end with a few observations as to how we can get to the transformed state from here. And in slide 24, I'm sort of saying here that the situation wherein software is similar to the crisis in manufacturing management in the 50s, and Dr. Deming's 14 points of a transformation to new philosophy of management enabled the Japanese industry to outperform American corporations in steel, auto, and electronics industries. And so I kind of encourage those of us in the software business to review Dr. Deming's work and see the relevance of those 14 points to today's software state of the practice. And you will find that some of the same philosophies we talked about here in terms of what our journey that we took in our company, in terms of empowered engineers, in terms of making realistic commitments, in terms of having constancy of purpose towards a goal of very, very high quality on predictable cost and schedule, and having the vital few data to help us get there. Slide 25, I'm looking at it on a national scale to say that we need massive public and private funding to reskill a lot of our current journey workers so they can have the competencies for secure software development. I also believe there's a tremendous opportunity to create the next generation workforce in software development by innovative apprenticeships and other earn while you learn kinds of model and certify them for secure software development. And that itself could be a separate topic that I think maybe someday we'll have another webinar to discuss about. And that's sort of what I wanted to cover with you today in terms of talking about the unique opportunity in time and these main points that you see in slide 26 and challenging each one of you to work towards transforming your organization. And if our journey and our data and our experience is any value to us, I certainly would be very happy to see that we're able to contribute to the profession. And so I think that's basically what I had. We have our contact information here, both Dr. Curtis's and mine. Feel free to reach out to me with any additional questions that we're not able to cover in this 1 hour here today, and we'll certainly try and do that. So the next slide is, if you have any questions, I'll be happy to take them now.
Girish, thank you very much for a great presentation. For the remaining time, we've got about 15 minutes or so. My colleague, Tracy Berardi, will take over and manage the Q&A session. Tracy?
Yeah, perfect. Thanks. Hi, everybody. Good questions, some questions and general comments. First question. From what CMMI level can or should an organization apply this approach?
That's an excellent question. We would say, generally speaking, if you have at least some of the basics as the CMMI models, say at the level 2 where you have repeatable planning, project tracking processes, software quality assurance, configuration management, and so on, that gives you a pretty basic, some level of statistical control over the processes, and then you can continue to improve them. But the team software process and the personal software process actually can be introduced in an organization at any level for the most part. And we actually did it after we had gone through the CMM journey first, and we thought that may help us better. But either way, the focus is on teams and what the teams can do, and how do you give them the tools that they need so that they can make commitments that are realistic, that they can meet, as well as the fact that they're managing their work by quantitatively looking at data and so on, and collecting these very few metrics that the TSP and the PSP recommends that we do.
Perfect. Thank you, Girish. And here's a question that maybe both you and Dr. Curtis would like to address. I think it's a good one. Because the effort to create a correct line of code varies by 15-fold depending upon the complexity of the lines of code, why not use something like function points instead of lines of code?
Okay. Bill, you have some automated function point counting and so on that CISQ is doing, I believe, and if you want to take that, that's fine.
Well, CISQ, yeah, I'll turn it back to you in a second. CISQ has a international standard now through the Object Management Group for automated function points. And we developed that with a team led by David Heron, who's one of the world's gurus in function points, to be as close as possible to the International Function Point Users Group's counting guidelines. But we had to remove all the ambiguity in order to create an algorithm that could be automated. So that is now a standard. It's been out a few years. There are companies that that have technologies that will in fact do the automated counting. The nice thing about it is that with manual counting, it's not a measure, it's a random distribution, it's a random variable, because 10 different manual counters will come up with different counts on the same piece of software. Hopefully they're within 10% of each other, but when you're estimating, 10% is not particularly good. I mean, you look at Girish's data and they're down within less than 5% on a regular basis. So the manual count gives you the same answer every time on the same piece of software, so it's consistent. Over time it's cheaper. And so for people who want to use function points, that's a very good approach. Lines of code, the biggest problem that people like Capers Jones and others have complained about is the definitions are all over the place. In fact, I've seen and have demonstrated with empirical data that depending on how you define a line of code, you can get an order of magnitude difference in the results you get. You know, do you count data definitions, do you count blank lines, do you count curly cues and all that. But the issue there is that you set a standard that you maintain through the organization through how you count lines of code, what's to be counted, what's not to be counted. And if you do that, you remove most of all that variation. You can pretty much eliminate most of that. Then you get variation between languages that you can control with a weighting factor. So you know, it's possible to use lines of code. I've done it in corporations I've been in the past and get accurate answers. Many people now prefer function points because theoretically it gives you an answer more in terms of the user's functionality. But both when developed properly and counted properly can give you valuable ways of sizing. So Girish, let me turn it back over to you, and you can talk about why you chose lines of code.
Yeah, thank you very much. Good question, and the most important thing is really, number one, is get into the habit of measuring size and do it consistently, whether you do it with function point or lines of code. For us, the line of code was what Watts had worked with, and the PSB came like that, and we were able to define two things which are, I think, very important: a coding standard as well as counting standards. And that ensured for us that no matter who counts it, that there's consistency in that. And I also seen, Bill, and the questionnaire, the person that asked the question, I see in many cases where people are using lines of code and then backfiring it to convert function points and vice versa. So I think both are okay, as long as you do it and do it consistently and do it for the right reasons, and use it primarily for one. Another big reason is to normalize all of this data so that it is meaningful across small projects, large projects, and so on.
Yeah, let me add one thing, Girish. When you're in a maintenance and enhancement environment, especially if you're dealing with business applications, function points have serious problems because a lot of the work you may be doing is with the non-functional part of the code, which in a modern business application that has multiple languages and multiple layers and is supporting various technologies, a lot of the code, in fact over half the code usually is non-functional, and when you work on non-functional code, you don't get credit in terms of function points. Realizing that and wanting to try to help drive that area of measurement forward, the CISQ has produced a standard that is now approved by the Object Management Group as an official international standard they support for what we call automated enhancement points. So in a maintenance and enhancement environment, if you want to use functional style measures, but also need to account for work you do on non-functional aspects of the code, this is a very good measure. It measures both functional and non-functional code and then translates all of that into a measure that's more akin to what you get with a function point measure. But it does, we believe, solve an important problem when you're trying to use functional type measures in a productivity analysis in a maintenance enhancement environment. So if you're facing that problem, I encourage you to look at the new OMG standard for automated enhancement points. Tracy?
Great. Next question here, more of you might want to comment on this thought. It looks like you may be focused on reducing vulnerability of what's being crafted and not the vulnerability of the system that will occur when it's delivered and integrated.
Yeah, that's probably a good point too. But you know, it's kind of like this: if you take care of all of these very obvious ones, which take them early, the life cycle and prevent them from getting into the customer's hand in the first place, it's pretty good. But that does not necessarily guarantee that there may not be some other vulnerabilities actually happening during production. But our experience has been that the majority of the defects happen due to errors that people make, because we're human beings, we make that. And the fact is that if you don't take them out as close to the point where you make them, then it costs a lot more. But your point is well taken. But we have seen that able to deliver, in one case we delivered 700,000 lines of code. In independent penetration testing, there were 0 vulnerabilities in the code by using these methods. So, and then that application is now has been in production for 4 years. It's had 0 downtime and no reported attacks against that. So that's sort of how we think that these methods, by combining the TSP, PSP, Agile methods with high maturity practices and these empowered teams, all the stuff I talked about, I think we're able to, so far anyway, seen that the vulnerabilities are not there for attackers to exploit.
Okay. Bill, any comments on that, or should I move to the next question?
Move on to the next question. Yeah, we've got time for maybe one or two more questions.
Okay. Girish, do you discern the team learning curve at all and then use that to reforecast the project?
You're talking about individual productivity or just the time? Okay, well, maybe we can ask a question here because people are not there. But I'll assume that that's the question is it the overall productivity of the work? And there is an investment up front in terms of the training that we have to do to get these people trained in these the TSP, PSP methods, which focuses on collecting the data, analyzing it, all of which they get in the training, and then they're able to actually use them in the project in a team environment. So, but we have some data that shows that within like 300-400 lines of code, you get all of that back in terms of the reduced rework time and the actual high quality that they're able to do. And it's also based on each person looking at their own data and seeing what it is that they're able to do relative to the time it took for them to actually get trained and become proficient on the job.
Tracy,
Next
let me add
question.
something. Let me add
Sure.
something to that real quick. If the issue is how do you build the learning curve into your estimating for a project, the fact that TSP actually does that for you to some extent by allowing the team to make their own estimates. I mean, people are saying this is how long I think it will take, and they can look at how much they know about the particular application or the aspects of it that they're building, and they build that into their estimate. So TSP incorporates that by having people with their own data from their own personal work process understand what it's going to take and build those estimates into the overall team estimate.
And this will be our last question here. In the ideal case, by eliminating all software defects, the security-related ones will also be eliminated. But considering that time and resources are limited, would it make sense to find, via system-level analysis, and fix the security ones with priority?
In fact, yeah, part of the defect tracking and classification thing is to identify priority levels of these errors, and the teams will address the most highest priority defects to take care of them. And then, but again, what we find is that by the time you get to the test, because there's only very few defects left in the code, the product, the teams are able to actually get much better yield out of tests also. And so what the customer sees is practically no defects or vulnerabilities in the code.
And Bill, if you have any comments,
Okay. You know, we do recommend that that when you get the results of any kind of analysis, especially system level analysis, you look at the application and prioritize the attributes for that application, and then use that to prioritize which defect, which vulnerabilities to fix first. Sometimes reliability be critical. For other applications, it could be maintainability. Security is always a huge issue, regardless of the application. So that would certainly go at towards the top of the list. So thank you for all the questions. I want to thank Girish for giving a superb presentation with some really fascinating data. Data I think people really ought to look carefully at, because there is now proof that TSP and PSP do work in the industrial environment. They can be integrated with Agile methods to produce some extraordinary results. And I'm glad that Girish had this opportunity to present that in this webinar. I also want to thank all of you for joining us and encourage you to go to the CISQ website, the Consortium for IT Software Quality, which is it's crazy I'm getting this backwards, it-cisq.org. You can become a member. It's free, and you'll get access to the standards, to white papers about how to use the standards. You can participate in the blogs and other kinds of things, and there'll be we're going to be starting in a few more weeks. We're going to have a questionnaire on the website where we're asking people to estimate the time it takes to fix various kinds of vulnerabilities. That's critical for helping us build a more accurate standard for technical debt, because the real issue there is how long is it going to take you to fix various kinds of problems, and what kind of cost does that entail. So again, I encourage you to go to the it-cisq.org website. If membership's free, just push the button right below the nice lady's picture and fill out some questionnaire, and we'll send you back a password. So thank you very much for participating in the webinar today. Thank you for the questions, and Girish, thank you very much for a great presentation. So with that, we'll adjourn the webinar.
Thanks, Bill. Thanks, Tracy, and thanks everybody for attending. Thank you.